It's Paul back with the final video for week 3. This one goes along with the second proof for the week, the proof that the only way a matrix can be invertible is if it's square. This proof has to be done by making general arguments about what happens when you do row reduction, and you might find it useful to look at a concrete example of the row reduction that's envisioned by this proof. I'm not planning to do this row reduction by hand, so I'm loading the practical math library, and I'm going to start up with the first and easiest part of this proof, namely the proof that in Rn there's no way that n plus 1 vectors can be independent. So I'm going to set up a matrix that illustrates this. In the case where n equals 5, I will have 5 rows. My vectors are in R5, but I'm going to have 6 of them, so I need a matrix with 5 rows and 6 columns. And rather than type in numbers, I'm using the result of the R function RUnif, which generates a random number that lies in between 0 and 1. So here goes my matrix. Okay, we've got the matrix. I wouldn't want to have to row reduce that by hand, but I'm happy to row reduce it by computer. There it's row reduced, and what happened? Not surprisingly, I got 5 pivotal ones. I couldn't have got more than 5 pivotal ones, could I? No way. There are only 5 rows, and you can't have more than 1 pivotal row in a 1. So there's no way that all 6 columns could have turned out to be pivotal. It might have been the case that the second column was twice the first column. In that case, the second column, not the 6th column, would have been non-pivotal. But there has to be some non-pivotal column somewhere. That non-pivotal column is a linear combination of the columns to its left, and that shows that this set of 6 vectors cannot possibly be linearly dependent. The other main ingredient of the proof is the fact that in Rn, n-1 vectors are not enough to span the space. And this turns out to be considerably harder to prove. This time I'm going to use n equals 6, so I have 6 rows, 6 component vectors, but I'm only going to have 5 vectors. Again, that's a total of 30 components, each of which is a random number between 0 and 1, only this time I provide a second argument of 6 to the matrix function, so I get 6 rows and 5 columns. So there's my vector. I want to row reduce it, but I know in advance that I'm going to have to talk about elementary matrices. And so I want to construct explicitly the product of elementary matrices, which we call E, that does the row reduction. I do that by slapping on the 6 standard basis vectors in R6. Those would be a pain to type in. Fortunately, R has a function called diag, and diag6 simply gives me the 6 by 6 identity matrix. So here is my gigantic matrix A, my 5 vectors followed by the 6 standard basis vectors. I row reduce this into a red. That's not a famous home run hitting baseball player, but rather a reduced A matrix. And it's not too surprising that we get 6 pivotal columns plus a bunch of non-pivotal columns. Now, originally, columns 6 through 11 inclusive were the identity matrix, and therefore the last 6 columns in this case are our matrix E. By using comma 6:11, I can extract them, and there's my 6 by 6 matrix. This does the row reduction. If I apply E to my original matrix A, I get as my first 6 columns the 5 vectors that have a single 1 in them, subject to some rather annoying row reduction, and then a bunch of junk. This matrix E, being a product of elementary matrices, is guaranteed to be invertible. There's its inverse, and now comes the tricky part. What I do is take the last column of this inverse matrix. The last column of that inverse matrix is the result of applying it to the 6th standard basis vector in R6. When I apply E to this W, I am guaranteed to get the 6th standard basis vector. But when I row reduce B in the 6th row, I get a column of zeros. And what that means is that the problem of solving the equation B times X equals W is impossible. There is no solution to that, because when I row reduce, I say this bottom row means 0 times my first vector plus 0 times my second vector on up through 0 times my 5th vector equals 1, and that's impossible. I agree, it seems obvious that 5 vectors cannot span R6, but if we want to prove that, we have to construct a vector that cannot possibly be a linear combination of our 5 vectors, and we have to show that we can do that for any 5 vectors, and this is essentially the only way to do it. Now we can cash in the results we just proved and show that an invertible matrix has to be square. What does it mean to say that the matrix A is invertible? It means that if we write down the equation A times vector V equals vector W for arbitrary W, a solution has to exist and it has to be unique. Suppose we had too many columns. So I've now set up a matrix that has 6 columns, and I put some arbitrary W on the right. I row reduce, I look at this, and I discover to my dismay that the 6th column is non-pivotal. That means I can assign any value that I want to the 6th component of the vector V. That means my solution is not unique. Second case, suppose I don't have enough columns. Suppose I continue to use 5 rows, but now have only 4 columns. I help out RRef by giving it an extra unnecessary column of zeros on the right, and I've now set up to solve the vector equation AV equals W by row reduction. But when I look at the bottom row, I see that it means 4 times the first component plus 0 times the first component plus 0 times the second component, and so on, is equal to 1. There's no way that that can happen, so the solution does not exist. And now we've got it. If we have too many columns, then the solution cannot be unique. If we have too many rows, the solution does not exist. And therefore, the only way the solution to AV equals W can exist and be unique is for the number of rows to equal the number of columns. And we have finally proved that the only way a matrix can be invertible is to be square. Being square is not a sufficient condition for invertibility, but it's a necessary condition. John Hubbard is quite proud of this proof and maintains that fundamentally this proof has to be included in any treatment of linear algebra, no matter how abstract. Now there's a slight problem with the second part of my proof, I might accidentally have chosen a W on the right-hand side that happened to be a linear combination of the 4 columns. If I want to guard against that, I have to append a 5 by 5 identity matrix and go through the row reduction argument again. There's the matrix that row reduces A, and if I solve the equation E times the last standard basis vector equals W, then I find a vector that always works, and the reason it always works I've already shown you. When I do row reduction, that vector that I've constructed by applying E inverse to W is guaranteed to get converted by row reduction to the last standard basis vector, which sits opposite a row of zeros to its left and proves that there is indeed a vector that's not in the span of the columns of the matrix.